Waiting for anyone.
I think we can start. I think Shree's out and Sean out as well. So why don't we start?
Okay, awesome. Let me introduce the speaker first.
Thank you.
James Tompkin is an assistant professor of computer science at Brown University. His research is at the intersection of computer vision, computer graphics, and human-computer interaction, and it helps develop new visual computing tools and experiences. He studied his PhD at University College London on large-scale video processing and exploration techniques, and did postdocs at Max-Planck-Institute and Harvard University. And recently, he has developed new techniques for low-level depth reconstruction, video synthesis for VR, and content editing and generation. So, James, thanks for coming. And all you.
Thank you very much. Hi, everyone. Can everybody still see the display?
Yeah.
Ish.
Yeah.
Okay, I'm gonna stand.
Yeah.
I have to come and like press this button repeatedly. Okay, okay.
Nice.
Yeah, I can see.
Okay.
Yeah.
All right, so hi, everybody. I'm James. It's a pleasure to be here with you all. Actually, there's quite a few different Columbia connections that I just thought I would enumerate. Steve Feiner used to be a Brown student working with Andy Van Dam. And then in the past, I worked with Changzi Zhang, who I guess is not on this floor, but he's in over that way. Yeah, okay. Back in 2015. And then Yon Fei, who worked with him at that point and that time. This is all before you. And then let's see, one of my students right now is also a Columbia alumni. She worked with Sharon Song. This is Yiqing Yang. So I owe you a debt of gratitude for that. What we do in my lab at Brown, it relates to these things here. So historically, and now pretty much every camera that you buy is some kind of multi-camera system, right? We no longer think about single cameras, but we think about camera systems, okay? And so we try to build capture and editing tools for multi-view images and videos, okay? Today, I'm going to talk about two projects that are to do with multi-view imaging. Here's the little teasers. The first is about depth. We know that depth is fundamental to many of the tasks in visual computing that we want to accomplish, right? And modern smartphones now have time-of-flight sensors on them to help us improve this situation. What you see on the left is the derived depth from a real time-of-flight camera, but it's got some problems, especially to do with noise and resolution. And on the right-hand side is what we're able to accomplish with some moderate processing. Let's leave it at that. And then the second thing I want to talk about is beyond better cameras, but how we can do better reconstructions with more cameras. Suppose that I had captured many images of this scene, and I wanted to be able to produce a view synthesis method to produce very high quality reconstructions of views of this indoor scene. So we're going to talk about how we can scale neural radiance field methods to be able to cope with thousands of images over large areas rather than just representing a single object. Okay, here's how I think about the world slide. So the planoptic function exists, right? Light is everywhere, except in the dark. And then we capture it with cameras. We sample subsets of this planoptic function with all of our multi-camera systems. And this does us the disservice of producing a 2D image, right? And what we actually want out are these representations of geometry and lighting and material that we can manipulate or edit to be able to produce new graphics or analyze them for vision techniques, right? Once we have those representations and we've made those edits, then we typically synthesize another 2D image to get put out to a display that adds to our planoptic function with its new light. And then our human being goes and edits or interacts with this media on maybe a 2D display, maybe a multi-view display, or maybe even in VR, something like that, right? We know that this analysis branch here is incredibly difficult, right? That's why we're all in the room, right? These are significantly ill-posed problems. If I want to reconstruct the geometry, I have to unproject somehow, right? And teasing apart the materials and the lighting is even more complicated than that, right? It's just unknown where I can scale the lighting or I can scale the reflectance of the material, right? So we have to do something. Unless you've been sitting under a rock, our community has undergone a significant change through the introduction of these neural field methods. Sometimes we call them like coordinate-based neural networks as well, right? I did not understand this at all, okay? Okay, so to try and help me understand this, my colleagues and I were kind enough to let me try and help out on a state-of-the-art report on these neural field methods, okay? And this was published last year in Eurographics. And then we also gave a tutorial at CVPR, and all the slides are online and the recordings and stuff like that. Because I'm an idiot, we made a promo video, right? Because this is you wandering wistfully through the fields of wheat, thinking about all of these papers. And then here's us, our combine harvesters, trying to make sense of this for you in this state-of-the-art report. And you can be satisfied at the end, eating your sandwich. Okay, so along with this, yeah, we're idiots. Along with this, we made a website. The website is quite neat. Whoops. You can search for papers. You can drill down to, for instance, only show papers with code, only show peer-reviewed papers. That's useful if you want to, in your rebuttals, mark what was contemporaneous and what was not. We're up to 363 papers in this database right now. And my favorite feature is the fact that you can click a button. I think it's that one, and it copies the bibtec for the paper onto the clipboard. And you can paste it into your overleaf. If you have work at ECCV that's to do with neural fields, or there's past work that is to do with neural fields that we forgot to include, please let us know. You can request a GitHub pull request. Or there's a Google form if you want us to do some more of the work to add it into the database. Okay, so from this, we came up with what we propose as a general framework for how we think about neural field reconstruction problems, right? We have some kind of sensed image from a camera, like an RGB image or a depth image, and we're going to call this the sensor domain. This is what we can measure, right? And what we really want is some other domain. In our case, it's typically radiance fields or density fields, right? But it could be sign distance fields, or it could be some other field. It could be to do with MRI machines or something else, right? And this is what we want to reconstruct, right? So typically these methods start by providing a sample in some coordinate space over space-time, and then feeding this into a neural network, such as a multi-layer perceptron, that's going to be asked to predict the values within the reconstruction domain at that particular point sample, okay? The bridge that takes us from the reconstruction domain to the sensor domain is what we call the forward map. And these can be anything, any kind of process that takes you from the reconstruction domain to the sensor domain, but for us, it's typically some kind of differentiable renderer, right? So in the case of radiance fields, it's a volume rendering, and in the case of sign distance functions, it's a sphere tracing algorithm. And because these are differentiable in their implementations through these amazing autodiff platforms, we can backprop a gradient through to the weights of the MLP such that we can optimize this to reconstruct the domain we actually care about. And if you want to change the output or vary the output of the MLP to perhaps represent multiple different reconstruction domains, then you might have some latent conditioning variable Z that also goes in to, let's see here also, that also goes into the neural network. And you might also have some kind of hybrid spatial data structure, maybe some kind of voxel grid that also helps you separate out different parts of the scene with respect to the neural network. So today I'm going to talk about two projects one that's going to introduce a different forward map than we're used to, and then one that's going to look at how we can build hybrid data structures for these large scale scenes. All right. Doing okay? All right. So let's talk about dynamic scenes. Dynamic scenes are hard when you only have one camera, right? Because typically when we want to reconstruct the scene, we exploit the fact that we see the same thing from different views, right? And in a dynamic scene, if you've only got one camera, you never see that. The scene is always changing with respect to the camera, right? And so Google, for instance, went and built this super neat multi-camera rig to go and capture these immersive light field videos. But one thing that's in our favor in the monocular case is time-of-flight cameras in new smartphones, right? Well, I already showed you that their outputs are not that great. The noise that you saw at the initial teaser often affects the reconstruction in significantly bad ways, right? Especially for dynamic scenes. This actually is a static scene and it's just the thing moving around, right? So what we want to try and do is get rid of some of the problems with time of flight by introducing a new forward map that's going to augment our existing neural volume rendering approaches, okay? So you might think, well, can't I just use the depth that comes out of the sensor itself? And the answer is, if you do that, you're doing it wrong. The depth that comes out of the sensor already has the errors baked in, right? Which means that if you use that as supervision for your reconstruction, I can't help but overcome, I can't possibly overcome those errors, right? So we're going to see if we can do this in a different way. This project is called TURF. Yes. Ben and Elliot and Aaron were all my students at Brown at some point, and then Ben is now a PhD student with Matt O'Toole at CMU. I know you might need a bit of revision on your German linguistic assimilative vowels. So when you put the O next to the E, it makes the sound so that it rhymes. TURF rhymes with nerve. Okay. So here's 3 errors that are common in time-of-flight signals. On the left-hand side, you see the input scene and then the depth derived from time-of-flight. And the top of this monitor here, or the back of that monitor there, is very, very noisy. And you get these values that look like they're extremely close to the camera, right? They must be wrong, right? We know that they're wrong because the top of the monitor isn't significantly closer. In the second case, we have biased results from multipath reflections. So depth cameras typically make the assumption that the first surface that the light hits is the surface of intersection, was the only surface of intersection. But when you're dealing with reflective objects, that isn't the case. The light has bounced from somewhere else before it bounced into the camera, right? And so you see that the reconstruction in this region is very noisy, unreliable. Okay. And then the third one is some kind of range issue. In this scene here, Ben is pretending to photocopy, and in the background, it's slightly farther away, but it looks like it's super close to the camera, right? And so this is a huge problem as well, and we'll learn about why that is. But these are the results that we're able to achieve. These are novel view renderings of that particular scene, and that scene was captured with a single camera system, right? Just moving through the scene like this, like handheld motion. Okay, we need to understand 2 things to really get to grips with this. The first is how to integrate time of flight into our neural volume rendering. And then the particular way that we're going to do this is with these things called phasor images. And we understand why that helps us in the reconstruction. Okay, you're probably all sick of this slide. It's the slide that tells you that a neural radiance field has radiance at a position in a direction, right? And then it also has density at that position. And to produce an image from the radiance field, I'm going to integrate from point samples along the ray. I'm going to use quadrature to estimate the function in between so that my integral is well formed. And then I have these 3 terms in the integral itself. I have a transmittance term, which is the part that gets accumulated as I step through the points along the ray. I have the density at the particular point, And then I have the light that is heading in that direction towards the camera that is emanating from each of those points. And when I solve this over the length of the ray, where the length of the ray here is t, from the near to the far plane, I get the value of the color that ends up being integrated on the pixels plane. Okay, this is a really useful form because if you replace the luminance at the point with the distance along the ray at the point, you get the rendered depth. Okay. This is not how time-of-flight cameras work. Okay. So what we're going to do is show that this naive approach for what depth can be produced is incorrect. So here's a basic kind of time-of-flight sensor. It's called a pulse time-of-flight or direct time-of-flight. I have a light source that emits a signal into the scene. That light is reflected off the scene and back into the camera, right? And because I know the speed of light, and because I can measure the time it takes for that light to return, it must be half of the distance must be half of that, and so I get my depth. All right, this is like a LiDAR system. Right? Okay, so let's build an integral that represents what is going on within this image formation model. We're going to bring the color in again, which we're used to, so that you can compare the two, right? Okay, so now instead of the light being emitted from a point towards the camera in the color version, the light has to come from a place, bounce, and then come back into the camera. This particular form, we're just going to assume that the light is in the same place as the camera for convenience, but in the real model, we can cope with that. So what has happened, now I have had to square the transmission term because the light has to travel twice through the volume. And so at each point, that transmission is multiplied by itself. And then we have an inverse square fall-off term because only some of the light that gets emitted will return simply from the geometry of the area that's subtended. I have this 1 over r term where this is the distance along the ray. So just less light comes back because the area subtended by the light that's hit in the scene is less towards the camera. Okay, and then we're going to say that the density is the same. Typically in in time-of-flight cameras, you use the infrared part of the spectrum. And it's a little bit of a fudge because sometimes things reflect differently in infrared light than visible light, but we're going to go with this. Okay, and then instead of light emanating from a point, now we have a scattering function. Some portion of that light will be reflected at that point back into the camera based on the reflectivity of the material itself. That's this IS term. Okay. All right, so we're most of the way there. We're going to introduce now a convenience function that's going to let us model multiple different kinds of time-of-flight sensors. This function we're just going to call W, and it relates to the length of the path that the light has traveled. So this x minus xt is, here's xt, here's x. It's just twice the length. Okay, so in a direct time-of-flight system or pulsed time-of-flight, you can think of W as just being like a one-hot vector, where at some point the light returns and you see the light, right? And so the travel time tau is just at some resolution of my clock when the light returns. Okay, and then from whatever that one-hot vector is, I can then go and compute the distance from the formula that I had before. Okay, that does LiDAR. There is a second kind of time-of-flight that is very common, that is called continuous wave time-of-flight. This is a method that can be more robust and more cheaply manufactured than LiDAR systems, and you can build them in big arrays, so you get high-resolution images of depth. Okay. Okay, so why is this different and interesting? So now instead of sending out a pulse, the light source emits a sinusoid of modulated light. So the amplitude of this light varies over time. And some of it comes back. And you can see that there's two things that have happened from the light that's returned. One is that there's a phase shift in the modulation of the light that comes back. Right? This relates to the distance that the surface is from the light source. Okay, but you immediately note that the pattern repeats, and so I'm only going to be able to detect the distance based on this phase difference within one period of the wave itself. Right? There's an ambiguity as to which of the wavelengths I'm in. Okay, and then the second thing that you'll note is that the amplitude is different, right? Some of that light didn't get returned. It got absorbed by the materials in the scene. And we can relate those two concepts through this formulation from Mohit Gupta called phasor imaging. Here is where we change the path length importance function. Okay, and you have to remember your high school maths for this bit. Do you remember Euler's formula? Euler's formula relates a complex exponential to, over time, to the sine and cosine. Okay, and so we can represent this modulating function in this particular form, where we say that the phase that gets returned will be based on the distance, the frequency, and the speed of light. Okay. All right, so this determines what our phase will be based on what is in the volume. And all of this part tells us what the amplitude will be, because all of this just relates to how much of the light is coming back. Together, this is represented as a complex number. This is called the phasor. Okay, and so that complex number represents both the amplitude and the phase. This is the model. This is the forward map that can model different kinds of time of flight data. Now, I said that existing time of flight cameras just look at the first surface of intersection, right? That they can't do this multiple bounce thing. So if we relate this integral, which we know is going to integrate positions in the volume, for a regular time of flight camera, it would just look something like this. The first point of intersection would be y, and I'm stuck at that point. If I have multiple bounces, I can't really model where that light has come from. So this is a less principled way of modeling what happens to that light as it's emitted into the scene. Okay. So now we have to understand why this helps, right? This is the model. Why does this help? Let's look at one of these phases, again, using Euler's form, using our notation of a circle, and this is a vector in the real complex plane. On the left-hand side, you see the amplitude and the depth, and here's our Stanford bunny that's going to move back and forth, and we're going to see what happens to the phasor. The phase is the angle of this vector, and then the amplitude is the magnitude of this vector. Okay. All right, so as the bunny moves back and forth, we see that the value of the phasor changes, its angle changes, and its magnitude changes. Okay, and we're going to use this visualization to explain how we can avoid the problems that we saw right at the beginning. Okay, I just need to tell you one more thing about the actual reconstruction problem that's solved. We take the RGB image from the camera system, and we take the phasor that is produced from the time of flight system. We don't take the depth, we take the phasor. Right? And then from these joint signals with that shared density, we're going to reconstruct the volume. And then from that, we're going to render with our forward maps what the RGB image looks like and what the phasor image looks like. And then penalize the loss between the two to optimize the network. Okay. All right, so the noise. Let's come to the noise. When you're in phasor space and you have low reflectance in your scene, black objects, the loss is already automatically going to be smaller because the magnitude of that vector is small. Can I push you over there? Sorry. No problem. Okay, let me say that again. Actually, I'll just skip to the graphic. Okay. When I have a dark object, less of that light comes back, right? And so that the magnitude of this vector will be small. That means that when I have to penalize a loss, its relative contribution to the RGB image will be less. So you can think of this as like automatically trading the two signals that are coming from the RGB camera and the time of flight camera. It just happens by itself. It's like automatic confidence weighting. Okay, and then in our reconstruction, we have much better characteristics. Obviously, it's still not perfect, but those significant regions that are meant to be previously super close are now gone, right? And the back of the monitor is much smoother. Yes.
Isn't there black objects in RGB channel?
That's right. And so at that point, you're looking at the specific like sensitivities of the different sensors that you have in the system. So they could have different signal to noise ratios, for instance, and be more or less sensitive to light. Yeah. Okay. Yeah.
I have a question. So why is it preferable to deal with noise in this like Bezier space as opposed to just like in the depth space? You were saying that depth.
Yeah. If you could predict confidence in and give that as well as a signal in depth, that would also be fine. You could also do that. Then you could downweight the points that you thought were not confident. The interesting part is that it happens automatically by the formulation. Yeah.
Thanks.
You're welcome. All right, let's go to the second one. Oh, yeah, sorry. I have a comparison slide. So the input sequence, these are the novel views rendered from the scene. This is a method that uses a comparable approach, but previously had a classical depth supervision. You would do like a classical depth reconstruction and then pass that in as well into the same kind of formulation. And in here, we swap out its depth processing for the depth that comes straight from the TOF camera. Okay, so this is what result you get if you just use the depth that comes out of the TOF camera. This is the result you get if you use the phasers. And you do the proper volume integration. Okay, and you can see that this is crappier. There's more noise that gets put into the reconstruction. I think that's a technical term, right? Cruft. Should I use a different technical term? Okay, let's go on to the second one. Okay, we had the multi-bounce interference, right? Okay, we never explicitly penalize depth derived from time of flight. We only penalize the phaser space, right? And so we never have to make a hard decision about what the depth is, right? So here's the illustrative example. We're going to place some kind of transparent object in between the camera and the scene, right? What we end up with is a superposition of the light that gets returned, because half of the light might be transmitted and half of the light might be reflected, right? And in this case, just with the classic formulation, you're screwed, right? And in this case, you just say, I don't mind. The reconstruction can put density wherever it likes, as long as the product is returned, the product of the light. And so in phaser space, that's fine. That's fine. And so this lets us be more robust to this multipath interference stuff. And so now it's kind of blown out on here, but what used to be noisy is now not noisy. Yeah, I think it's also the display itself has like super high gamma or something. It's okay, we can turn the lights back on. On my laptop afterwards, what happens is that you actually get to reconstruct the multi-bounce appearance so that you see the doors opening and closing in the shiny reflectance of them.
And those doors were glass again or no? Those
like polished aluminium,
okay.
aluminum.
Yeah.
Okay, here's another example with the glass. You see that we have less of the cruft. Like you see some of these reflections get put onto layers of depth that are too close, right? We still don't do a perfect job. Ben is carrying a laptop, which is low reflectance, it's black, and it's moving, and all bets are off, right? You can see that the original depth camera has no clue what is going on that particular object, and none of the reconstructions are very good in that. But okay, we did slightly better, less noise in the reconstruction. Okay, last one. We talked about the phase only being valid up to one wavelength, right? Which means that stuff that's out of range you have no clue about. We call this the unambiguous range and the ambiguous range, right? And those depth errors were caused because they were in this ambiguous range. Because we share density between the time of flight signal and the RGB signal, there's only one solution to where the surface is that matches both the signal from the RGB and the signal from the time of flight. Okay, and so we automatically select the right distance and overcome this range ambiguity problem. I'll just let that sit. Did that make sense? Sort of, but not right. Okay, so suppose the signal comes back, right? And it just so happens that I'm in the wrong period. I'm actually at like 4 pi instead of 2 pi, because the signal looks exactly the same at 4 pi than 2 pi, right? And so one might be at 5 meters and one might be at 10 meters, right? To the TOF camera, they look identical, right? But only one of those looks like it's at 5 meters to the RGB camera. And the optimization just resolves this. Okay. All right, so here's the actual example. If you look at the depth output, which is the classic TOF depth output, as the phase increases, there's an equivalent phase when the bunny is close and far, right? Which means you, with a continuous wave time of flight camera, you can never get that. You're always bound by the range. Yeah.
This might be a little bit contrived, but what if the RGB network just happens to predict the same color as well at the next yard? Like, is there any way from this network learning to make like a bigger copy of the entire room, but then
No.
5 meters squared or something?
No, I think because it only has to explain it once to the camera view. If you could somehow construct a situation in which there had to be 2 copies in the captured views to be valid, right? Otherwise, I don't think so. I think it would just produce one reconstruction, but at the wrong depth,
Okay,
or arguably maybe at the wrong depth.
I see.
Yeah, I don't think there's a world in which it would build 2 copies of the thing, because you still have to project those both down to penalize a loss against a 2D image. All right, here's the comparison where we use the raw depth, and you just, you're hosed. You can't really do anything. Yeah. Yes.
These depth maps look really clean. Are there any priors, like sparsity priors on it,
No.
or is it really just a better forward model?
Yeah. Well, the other thing is that you're doing active sensing.
Yeah.
So the gap between what you can do with priors and what you can do with active sensing is huge. This is the slide for that. These two both use priors. They're both different kinds of priors, right? NSFF is -2, monocular depth prior. I can't exactly remember what the original one for. Oh, this is a classic reconstruction-based method, right? There are certain situations where you just want to use active sensing, right? When you have any kind of stereo system and you're looking at a blank wall, you definitely want. Yeah. Okay, let's. Oh yeah, sorry, I have to say limitations because it's not fair of me to say things without limitations. We said low reflectance dynamic regions are still problematic because there's no real correspondence that can come from those, even as you wave the thing around. And then the second is that in the monocular case, sometimes, you always have disocclusions somewhere. In a multi-camera case, the disocclusions from one view are covered by another camera, right? But in the monocular case over time, there's always a disocclusion somewhere. And so you see that Matt has like a shadow head behind his head in the reconstruction. And to really solve that, you would have to solve correspondence properly. Okay. All right, so that's TURF. So more principled physical modeling of time of flight sensors to give us just fundamentally more robust depth. It's super expensive right now because you have to solve it through a radiance field, right? If you could make that fast enough to run it on the device, it would be super great for things like AR. All right, I have about 15 minutes. So that's the better camera. Okay, now let's think about the more camera. What we want to do is scale neural field methods to large scenes. That's the goal. And provide us with efficient optimization, or at least parallel optimization, and interactive rendering. That would be great. Okay, so this is work, skip that. That came about, I went to visit Qi Jinghuang at UT Austin last summer, and he put me in touch with his people doing image-based rendering. This is Wei Wei Zhu's lab at Zhejiang University in China. And this is primarily the work of Zhu Chaowu and Jiamen Xu, who are amazing. All right, so we want large realistic scenes for many of our applications in visual computing, right? VR or telecommunication is a great example. We don't necessarily all want to be just living in black voids. So when we start to reconstruct a space, the first thing we typically do is go and capture a bunch of images, right? And the ultimate quality of our reproduction will be determined by the number of images that we take, right? If I could densely sample the whole space, I would have a perfect reconstruction, right? So I want to somehow minimize this as well. I'm going to run this through a photogrammetry pipeline that's going to produce me the poses of the cameras and also some kind of proxy geometry for what the space is, okay? Classic ways of producing interactive walkthroughs for these kinds of scenes might be to use image-based rendering. So in image-based rendering, you project each of the input source camera 2D images based on the proxy geometry into the view of the virtual camera in yellow, and then you try and blend them together. That's classic image-based rendering, right? Reproject the input views. And this is scalable, but doesn't produce particularly good results. So you can see that it seems to, like, the highlight here seems to jump between positions, right? And that's because it's jumping between the input source views, right? And even if you use deep features, it still doesn't come out quite well. And you can see that there's sort of flickering in the scene as well, right? It's not particularly stable. If you go and try to do a more principled modeling of the lighting and the material in the scene, you can get something that looks like this. This is from George Droutakis' lab at INRIA. And it lets you do relighting as well, which is super cool. But you can still see that the geometry on some of the objects is not quite right. The reflections are better, but not really what it looked like in the scene in the first place. Okay, we're not going to do relighting, which saves us a bunch of headaches. We're just going to do view synthesis. But we can end up with something that looks like this. So the geometry is still pretty good. The reflection is stable and smooth and more accurately reproduced from the input photographs. Okay, and here's just a side-by-side. Okay, so how do we do this? There are 3 problems that we're going to try and tackle within neural radiance fields in the reconstruction and the rendering to be able to scale these methods to produce high-quality results on large scenes. The first is that the scene detail is limited by the capacity of the neural network, okay? If I took a larger MLP, it would take me an incredible amount of time to train it to convergence. And what you often find then, if you can't train it to convergence, is that you get, especially on reflected regions, you get blurred reconstructions. This is actually a window pane in front of these shutters here. Or around the specular reflections, you get blurring, things like this. The second problem we need to solve is that we have sparse input. So oftentimes when you reconstruct a neural radiance field, you have this kind of camera setup. Okay? And the cameras are close together, which means that you can actually sort of get away with interpolating the specular reflections, and it looks quite good. Actually, it looks great. But in the sparse case, you're really struggling. Here's an example. This is a part of the scene, which is a painting that has a glass pane on the front to produce a reflection, right? And you would think, well, I'm sampling quite a lot in the scene here, but of the 27 images that sample the painting, only 8 of them actually have the reflection. So, okay, so immediately if I'm penalizing a mean squared loss over something, it's going to be lower if I don't reconstruct the reflection than if I do, okay? And so actually it disappears. Okay, third problem is super slow. As my scene gets larger, the camera ray must be sampled with more points, right? And so I somehow need to break this relationship between the size of the scene and the number of points that get sampled. Okay, for scalability, you're all visual computing people. You're probably thinking, I know how to do scalability. I'm going to use tiles, right? Oh yeah, tiles. We use them for everything. Like image compression or rendering, right? It's just a generic solution. I'm just going to chunk the space and solve subproblems, right? No problem. All right, how can we apply this? Well, there's a few different approaches. You might say, the MLPs are really the problem. I'm going to get rid of the MLPs, right? And I'm just going to build a voxel space. And then at each vertex in the voxel, I'm going to have an RGB color. And then to represent the view dependent color, I'm going to have second order spherical harmonics. Okay, that's a lot of memory because they have to store 27 coefficients at every vertex location. And in a big scene, I'm again stuck with this scale detail trade-off because I'm bound by my memory use. Okay, and if my scene is so big, I might end up just not being able to fit it into memory. Okay, so let's get back to the MLPs. MLPs are really good at compressing things, right? Okay. What if we have one MLP per tile? That seems good. But no, not really, because now the optimization for this tile is dependent on all of the other tiles because the points must be sampled along the ray, and the ray is going to intersect many, many tiles. Right? This can be a good strategy. Maybe you've seen KiloNerf. It has lots and lots and lots of little MLPs in these tile structures, right? But what happens is that you train a big monolithic MLP first as like a teacher, and then the little ones get to train off the teacher. So you have to still produce the big reconstruction with the MLP first. So you can't really apply this approach either. Okay, what if each MLP could somehow encode its own background? The background being these points here, right? That would break the dependence. Right? I would be no longer dependent on other tiles when I cast a ray, right? So it's now independent in its optimization, but it's still not scalable because the number of points is unbounded. Well, it's bound by the size of the scene, but the scene is big. Okay. All right, so here's the cheat. The cheat is, well, where is the background? Well, we kind of know where the background is. We did this initial photogrammetric reconstruction, right? And for indoor scenes, bounded spaces, this is a pretty good assumption to make. So we're going to look at the geometry proxy, and we're going to find the intersection of the ray with the geometry proxy. We're not going to use that point. We're then going to take a range around where we thought the geometry was, but we know it's in error a little bit. And then we're going to sample that with a fixed number of points. So this is now independent because there's no dependency between tiles, and it's scalable in that the number of points that you sample is fixed. Okay. Then I train it. And I can do each one of these on a GPU, different GPU, doesn't matter. Okay. This is where it gets really cute, at least to me. These are the little sets of individual tiles that get reconstructed. We just put a few of them together, right? It reminds me of doll houses, like little bits of furniture. And they represent still the reflections and all the things that are going on in the scene. Yeah.
If each tile is independently trained, then wouldn't it create some discontinuity between the
That's right.
boundaries of-
That's right. That's right. If you have time, we can talk about exactly how we fix that later on. But yes, you have to do something. Yeah, that's very pertinent. Okay, if you just look at the geometry that came from the photogrammetry, this is the top here. It's pretty good, but doing this fixed number of points within a range of where the intersection was produces you better results. Like it fixes the problems that were in the photogrammetry in the first place and provides you with better geometry. You should be able to see the difference between the table lamp that was causing us problems at the beginning, right? Between its input photogrammetry and its final reconstruction. Okay, second problem that we were going to fix, the reflections. We were missing one. Okay, another cheat. Suppose I had a planar surface and it had spatially varying reflectance, right? It would look different from this point than at this point, But the reflection still comes from the same source. It comes from some ceiling light, right? And many materials are built like this. If you think of a polished wooden floor, the reflection actually looks about the same, even if the texture underneath is varying. So what we're going to try and do is split the view dependent from the view independent appearance. This is going to give us a simpler function to optimize for the reflection, especially if you have like blobby lights, things like this. The second trick we're going to do, when you think about light bouncing off things, you think about surface normals, right? Actually, estimating surface normals accurately is quite hard. Your geometry reconstruction has to be extremely good to be able to get that reflection to be in the right place, right? Okay, so we're not going to do that. We're going to skip the normal computation. And instead, we're just going to imagine that there are no bouncing and that there's a virtual light that exists underneath the surface. Underneath the surface? Yeah, underneath the surface. That we're then going to add back on to the view independent appearance. This is consistent with all of the rays of light. We just sort of unfolded them. Yeah.
This is assuming it's planar.
Assuming it's planar. Yeah. And for indoor scenes, that's also not a terrible assumption. There's a few tricks that we get to be it sort of work on slightly curved surfaces. A slightly curved surface is basically the depth of this point is wrong. So you can sort of fudge it for things that are slowly curved.
Like this bottle is.
Yeah. That bottle is an interesting thing to reconstruct. This is a technique that's been used in classic image-based rendering before. So I'm not claiming that this is new, just that it's good. Okay, so now each tile has two MLPs. It has one for view independence and one for dependence, right? And then the product of those two things is the thing that produces the final result. Okay, I know I'm running a bit out of time, so I'll speed up a little bit. This is perhaps my favorite slide. On the left is the combined output. On the middle is just the view independent component, and on the right is just the view dependent component. So you see the bright highlight on here. You also see subtle things like the reflections of the table legs and chairs in the floor, which you wouldn't necessarily think were that important, but actually go quite a long way to make it look like a real place. This is fascinating. Okay. And then the missing reflection, well, it's okay. It sort of comes back. It's not the crispest reconstruction. There's work like RefNerf that was at CVPR this year that spends more time doing better reflections, but we get some of the way there. Okay, the last thing. Now that I've split the two different components of the illumination, I can solve some of my speed problems. I can just store the view independent or diffuse component in an octree, get rid of the MLP, and then I can do very fast voxel rendering without any spherical harmonics for the reflection component, the view dependent component, because that's memory intensive. But I'm still going to keep the little MLPs. And these can be quite small because the function for the reflection is now simpler. It doesn't have to do with any of the diffuse component. So you can fit these in the tiny amounts. Actually, it's not that tiny. That's in CUDA shared memory on CUDA cores rather than in main VRAM, so that it never has to cache back and forth for each block. And so that's super fast. And so then you can do like 20 frames a second, 1280 by 720 on a big GPU, Yeah. How many such scenes?
Yeah. Oh, I didn't look at the paper.
No.
Yeah, I can look at it.
I don't make my audience look at papers. Okay. So the bottom one here is 150 square meters. And to apologize for introducing imperial measures to you all, that's 1,500 square feet. So it's not perfect. There's some fluffy stuff on this girder here. Sometimes the poses aren't particularly good, and you get blurring on high frequency patterns, like the tiling here is sometimes a bit blurry, right? But overall, it does okay. It does okay. Yeah. We were a bit surprised, actually.
Are these real capture data set or?
Yep.
Okay,
Real capture data set.
I mean, the quality is so good.
Yep, these are all real spaces. This is Jamin's apartment. This is a coffee shop. This is like a film studio bar scene. Somehow there was a movie studio near the university. And Jika and Jamin went down and just imaged it. So like, that's not a real croissant. Yeah, okay. Okay, I just have to get through some limitations again, because it's not fair for me to say that this thing is perfect. Whoops. So for tile consistency, we have to do some post-process to fix some of this. There's some training steps to help minimize it, and it's still not perfect. And there's some post-process that has to happen. I talked about the blurring on the high frequency details because the original camera poses are not as good. We've seen work that tries to optimize these within the loop as well. We talked about the phantom and the fluffy geometry that sometimes appears, also partly because of the camera poses. The high frequency of the reflections is still sometimes difficult. We didn't produce a very good reproduction on that. And obviously it's still limited to planar surfaces, and actually curved surfaces we have some trouble with. But otherwise, it does okay, yeah. All right, I'll stop there. So we talked a bit about neural fields, and we had this state-of-the-art report that hopefully might be useful to you, and send us your papers and we'll add them to the webpage. And then we talked about better cameras through more principled modeling of time of flight, through active illumination, through changing the forward map within the general framework. And then we talked about how we can scale to use more cameras to get bigger scenes by introducing this hybrid structure for the tiling and splitting the view independent from the view dependent appearance within this neural field structure. Okay, thanks very much.
Do we have any questions?
So it feels like both the time of flight and the scene doesn't generalize to outdoor scenes. Do you have any plans for?
That's a great question. Yeah. Yes. What things do you really care about? The luminance of the light itself is a problem. When you go outdoors, typically you have to work in HDR space. We played around a bit on some other projects with HDR data. It's harder to train in general because the range of numbers is just huge, and you actually care about quite a lot of that number range. But that's one thing that you would have to do. You have to be careful about like sampling the space at capture time a lot more, I think. This already takes quite a long time to go and capture a bunch of images. And so outdoor spaces, all of the reconstructions I've seen from outdoor spaces tend not to look as good, not because the method is bad, but just because you have far fewer photos per area to be able to reconstruct to a high quality, right? Like that coffee shop scene was like 1,000 images or something like that, right? So that's another problem. And then things tend to move when you're outdoors too. Like it's a slightly windy day today, and like already, you know, some like 5 degrees of my visual field is moving constantly by the trees outside the window, right? So that's also hard. Yeah. Hi. Yeah, you're welcome.
Very intrigued by the view independent and dependent separation.
Yeah.
What are your thoughts on the active sensing methods that might use polarization to separate it instead of learning it?
Yeah, it's super cool. Sony have a camera, I don't know if you know this, that has, it doesn't have a Bayer pattern. It has like 4 different polarized over the whole sensor. So you get an array estimate of the polarity of the light coming in. And it's only been on the market for a couple of years, if that. And I want to do that. I know that Ramesh Rashkar's lab at MIT has done a lot of work on polarimetric scene reconstruction, and most of that is in the lab still, like on an optical bench. So yeah, what's the constraint? When you know the polarity of the light came back, like 1 degree of the normal is constrained or something like that. So it's still quite a weak signal as to what the surface orientation is when you know the polarity, something like that. So it's not like a slam dunk.
Yeah.
But it's super interesting.
Yeah.
Yeah. When we've run out of other cameras to put on smartphones, like we might do that. Yeah.
I so I remember a few years ago you were interested in like light field
Yeah.
cameras, maybe still are, probably still are.
Yeah.
Do you see any exciting like nerve cross light field?
Yeah, there's been a few papers, right?
Okay.
Is
Is there anything in particular you're excited about?
So all of the, this is a more general comment beyond the light fields, right? All of the methods that we're producing now in the neural field space still have all of the fundamental problems that are inherited by the domain, right? Like the fact that when you point 2 RGB cameras at a blank wall, there's nothing that tells you the distance that that wall is away from you, right? And a nerf doesn't fix that, right? And so light fields are still very good at doing the things that they were always good at. They're extremely good at producing like accurate depth estimates. You can get amazing depth maps out of light fields. I should have brought some. But all of the constraints, like the fact that they still get fuddled by blank walls, that all still exists. Right? Light field parameterizations say that the only light that you care about is the light that hits some kind of proxy geometry that surrounds the scene. Right. So the classic, oh, I've got a camera, I've got a picture of one. Here you go. This is a light field camera. It doesn't look like one, but I promise you it is. So inside here, there's a lenslet array that makes a grid of like 49. It's like a 7x7 or 9x9 grid of cameras. Right? And you know the angle coming in because you can isolate the direction through what's called a 2-plane parameterization, right? And so now you can extend that to be like 2 spheres. So if you imagine a sphere and then another sphere around a scene, you pick any 2 points on that sphere and you define the ray direction that comes in, right? And so that's really cheap for building radiance spheres, right? But radiance spheres aren't that useful if you're trying to do reconstruction, because you actually want to know the geometry that's inside the sphere. Right? So for instance, light fields only ever tell you where the depth is at gradient edges within the light field. And so any other part within, you don't have an estimate for. Right? So they're super useful for certain things, like they're great for view synthesis. But for other things, they're still not useful. And that has been an intrinsic property of the format for a really long time. Yeah, so I'm like optimistic about the methods that we use, but all of the like things you can do with each particular camera setup haven't really changed. Yeah, which is somehow lost, I think, when you come into the field and you see all the amazing results and you're like, wow, we can do anything. And you're like, no, you can't. You're still bound by like, physics. I think I went off on a huge tangent. I didn't really answer the question. Yeah, light fields are still cool, but nobody makes them. Nobody makes light field cameras. If you want a really robust measurement of depth and you can't do active sensing, you want as many cameras as you can get. And that's a light field camera. Yeah. All right. Should we leave it there? Thanks, everybody.
Thank you. So James, I think